Hello everyone, welcome to my programming club. Today we will be solving another daily Leetcode problem, and the problem's name is minimum falling path sum. So you are given a n cross n array of integers, a matrix, and you have to return the minimum sum of any path falling through matrix. So what is a falling path? A falling path starts at the element in the first row and chooses the element in the next row that is either directly below or diagonally left right. Okay, and it will surely end on the last row of the matrix. So let's say this matrix is given to you. Then let me copy it here first. Yeah, it's fine now. So let's say this matrix is given to you. Then you can choose either of these one cell from the first row. Then whether then depends upon what cell you have chosen. Let's say you have chosen this particular cell. There will be three options. Okay, right now we are not concerned with whether these three options will be in the boundaries of matrix or not. For the convenience, I have chosen this particular middle element so that I will be able to show you the three options that we will be having. So the very first option that we will be having is this one, second option is this one, and third option is this one. Okay, so two diagonal options and one directly below. Okay, we are always to go in the downward direction, so rest all the options are eliminated here. So it's mentioned in problem statement also that three options will be there. You will also always be incrementing the row, but you will not always be incrementing or decrementing the column. Okay, so this is, if you want, we can write row plus 1 column minus 1. This one here is one row downward and same column, and this one here is one row downward and one column ahead. So these are the three options that you will be having. Then based upon what choice have you taken among these three choices, you will again be having three choices. Let's say you take this one, and then again three choices will be there, and it will continue again three choices, or say options. So in total, how many number of ways are there? First of all, let's see the constraints of the problem. So the length of the row or number of columns or number of row will be of order 100, and the matrix element will be ranging from -100 to +100, both included. So first of all, let's consider a worst case. You will be making the choice of very first element or first cell, that will be 100 C1. From 100 elements in the single row, first row, you will be choosing one, 0th row. Okay, so it will be 100. Then based upon what choices you have made, you again will be having 3 choices at each of the rows. So this was for the first row, or say 0th row in case of a zero based indexing, and these are for the subsequent rows. So let's say there were a number of rows, let's say are n, then it will be 3 raised to power n minus 1 into 100. So this n here is given of the order 100. So 100 into 3 raised to power 99. This will be the number of, or this will be the order of operations. Let me take it here. Order of operations that your program will be requiring, order of number of operations that your program will be requiring to solve the particular problem by trying out all the possible combinations. Also, this will be a brute force approach. So since you are trying all the options you are having, this will be a brute force approach. Let me write it here. Brute force approach. Okay. So this is the brute force approach. And this will be the number of operations your program will be requiring. Your solution or program. Okay. And it is very much greater than 10 raised to power 8 number of operations. This is a operation limit. If the number of operations in your program exceeds or become equal to this limit, then what will happen is you will get a TLE here, time limit exceeded, and your solution will not be accepted. No AC here. So those of you who are new to this concept, I will be providing a link of article describing how the time complexity of accepted solution varies according to input size. Okay, then you will be able to understand what this limit concept is all about. Right now what I can tell is, if the number of operations of your program is exceeding or becoming equal to this limit, then you may get a TLE and your solution will not be accepted. So in order to get our solution accepted, we have to optimize this brute force approach. We have to optimize it. So let's see what optimizations can be there. Let's take the next slide for our convenience. Let's copy the same example that we have copied previously. Yeah, it's the same example. So let's say you are in this particular cell at present. You are at present in this cell. So this is your current state while exploring choices. Okay, so somehow you landed upon 5. Now we will be seeing, we will be tracing our steps backward. So this is a key to solve these kind of questions. First of all, what you want to, you before that also you want to make two observations here. Let's say you decide to pick this path and then you followed this, then you went to 9. There is, this is one combination, let's call it combination 1. Let's call it combination 2. Let's say you decide to pick 1 first and then you went here, and then instead of going to 9 you went to 8. So as you can see, this part of these two paths or combinations is repeating. So we are having overlapping subproblems. What I mean by this is, you are, if you mark the rows and columns with indices, then what you are choosing is, first of all you are choosing 0 comma 1, then you are going to 0 colon, not 0, it is 1, 0 colon 1, then you are going to 2 colon 2. Okay, so this is the path you are following for combination 1. Let's call it combination 1. Now for combination 2, what you are doing is, you are following the same path as above till here. Now instead of going to 2 colon 2, you are going to 2 colon 1. Okay, this is 2 colon 1. So you are ending up here. So as you can see, this segment or say subproblems are overlapping in two combinations we are choosing. So we will be doing extra work here to calculate same overlapping subproblem again and again, to calculate result for overlapping subproblems. We are doing extra work. And this extra work is what which is leading us to TLE. Okay, so we need to eliminate this extra work. So we need to avoid this extra work. What we can do is, we can somehow store the results of the subproblems that are overlapping, and then when they will be occurring again, we will be using those results. Somehow store the results of overlapping subproblems and then use those results when they occur again. uh, when they occur again and again. Okay, so for the if you are seeing a subproblem for the first time, you will store the result. Let's say we store it somewhere. Then when we will be seeing it for the second time, this time you will be referring to this stored result, and you will not be doing work for this particular subproblem at least. So you will be avoiding extra work by this means. So this particular property of having overlapping subproblems in different combinations uh, is called overlapping subproblems itself. Okay, as the name suggests also. So this is property 1 that is satisfied by your problem. So your problem is having a unique setup which is satisfying this particular property. The second property which you can observe is second one. Let's say you have to form the result of 2 comma 2. Okay, let's say this is the result that you want to find out. It will be dependent on what previous choices have you made. Okay, so let's say we are adding the sums 1 and then 1 plus 5 6 and 6 plus 9, it will be 15. Okay, so you are adding so 15 will be dependent on what choices you have made previously. These are the choices that you have made previously. So right now what you can say is, by this observation, that solution of bigger problems can be formed by combining the solution of smaller subproblems. Let's call this subproblem 1. So this is also a solution of another subproblem, solution 2 and solution 3. So we can combine them and form the solution of bigger problem. So this is a bigger problem and these are smaller subproblems. This is bigger subproblem, you can say, or bigger problem. So solution of smaller subproblems can be combined to form the solution of bigger subproblem. This property is called optimal substructure. Now when these two properties are satisfied by a problem, then we can apply a concept here which we have just discussed, just storing the results and using those results to make the solution of bigger subproblems. This particular technique is called dynamic programming. Let me clear the board again. Okay, this particular technique is called dynamic programming. Storing the results and using those results to make up for the solutions or results of some bigger subproblem results, and at the end you will be having your final result. So storing solutions of overlapping subproblems and using them to avoid extra work and form results of bigger subproblems. Okay, I will also be providing a link of article describing this particular concept, and other two links will also be provided, one for overlapping subproblems and another for optimal substructure that we have just discussed. Okay, so these links will be provided. Now coming back towards our problem. Now you are having three choices. You could have been on 2 and then came on 5. You could have been on 1 and then came on 5. You could have been on 3 and then came on 5. So your current state is dependent upon three previous states. Your current state is dependent on three previous states. What are those states? First of all, you should be determining what are the variables defining the current state. So the current state variables are, let this be row, let this be column. So 0 1 2 0 1 2. So current state is defined by two state variables, row number and column number. So since there are two state variables, so the dynamic programming structure that we will be using to store our results will be of 2D. So it will be a 2D DP. So because two variables are there, so 2D DP is what will be using. Okay, so what we will be doing is, let's say your current state is, what name I have given to this, I think, yeah, path sum I have given. So just for the sake of consistency, we are considering path sum of r comma c. So we are at cell rc. This is your current state. So what could have been your previous three states? It could have been r minus 1 c minus 1, r minus 1 c, or r minus 1 c plus 1. Okay, so these previous three states could have led us to our present state. So these all are previous states. Three previous states possible. Okay, so this path sum will be We will be taking contributions from the previous state. Taking contributions from previous states. Whatever is the element at your current position, it is matrix RC plus contributions of minimum. Which state is giving you the minimum contribution, you will be choosing that state, since you are to required to return the minimum sum of falling path. So you will be taking minimum of previous state contribution. Okay, so those previous states are nothing but path sum R minus 1, C minus 1, path sum R minus 1, C, and then again path sum R minus 1, C plus 1. Okay, so whatever is giving you the minimum, you will take that and you will add it to the value of the current cell. That will be your answer for, or say result for, the current state. This is your current state. So we are having a transition equation, state transition equation at our hands. This is what is called state transition equation. So how the states will be changing, according to which equation the states will be changing. State transition equation. So this is what we will be using to form our solution. Now let's see the implementation. I know it's a long video, but I am trying to explain it for someone who is seeing for the dynamic programming, who is seeing this dynamic programming for the very first time, and how to think that you can apply a dynamic programming on a particular problem. So we are initializing rows and columns variables. Then we will be using this structure, this data structure, or say will be used to store the results of subproblems, overlapping subproblems, and use them to form the results of bigger subproblems and avoid extra work. Okay, and then we will be populating our path summary. Vector you can say, or array, depends upon the language you are choosing. So if it is the first row, then you have to pick one element from this row. And if it's not the first row, you will be taking contributions if it's not the first row, you will be taking contributions taking minimum of the contributions from previous states and adding it to current state and value of cell at current state. So this is what the current state value is, the cell that you are at, and these are the previous states. Okay, so this is your current state. Okay, and this is your current cell value, and these are your previous states. Okay, and let me zoom out so that you will be able to see it more clearly. I think it's fine now. And at last you will be returning what is the minimum sum at the last row. Okay, and this is how you will be solving this particular problem. If you are still having any doubts or any queries in general, then please feel free to use the comment section in the video. Thank you for watching. Have a great day ahead. And before ending the video, I forgot to mention the time and space complexities of this particular approach. So the time complexity will be order of n cross n, where n is the size of the matrix or the number of rows, and space complexity wise, since you are using a 2D vector or say array, it will also be order of n cross n. Okay, we can mention here n is the number of rows in matrix. Okay, so thanks again.